Hi everyone, this is Mrs. J, and today we're going to learn about linear approximations and differentials. Alright, I have a warm-up for you guys to try, so please pause the video. Alright, so check your work real quick. So we know to find the tangent line, we need to find the slope of the line at that point, which we can find using the derivative, and then we can just use point slope to make the equation. So we have the equation y equals 3x minus 2. Now today we're going to be doing what are called linear approximations. So tangent lines can actually be really useful for getting an approximation of a function when we're really close to that point of intersection of the tangent line. So this is called the linearization of your function at A. So essentially we're just going to take our tangent line like we did in the warm-up, and we would call that L of x because again this represents a linear function that can approximate our original function when we're close to the point of intersection. So here you can see that we have a series of graphs. So these are actually the two graphs from our warm-up. This is f of x and this is our tangent line. You can see that point of intersection. So here's that same graph, but zoomed in a little bit closer around our point of intersection. And then I zoom in even closer. And then if you keep zooming in, you'll see that the closer you get to that point of intersection, the more the original function, which you can see in red, it looks almost exactly like our tangent line function. So you can see that as you get really close to that 0.11, our tangent line is actually a pretty good approximation of f of x. They're essentially the same graph. So again, as we zoom in, our function flattens out and becomes increasingly similar to the tangent line. So we can actually use that tangent line to approximate a value of our function when we're really close to that point of intersection. The reason we might want to do that is because it might be much easier to evaluate our tangent line function than our original function. In the case of our warm-up, this original function is just a quadratic. It's not too difficult to evaluate, but if it were a much more complicated function, it might be extremely useful to use the tangent line to approximate a value. So let's test this out. We're going to use, again, from our warm-up, f of x. We have that 2x squared minus 1. And then we have our linearization function, which was 3x minus 2. And we're going to see what the values are for f of x and then for L of x. And we're going to see if they're close. So you can see these x values that I picked are really close to the value x equals 1. Because remember, we're really zooming in on that point of intersection. So why don't you take a moment, plug all these values into the function f of x and L of x, and let's see what we get. All right, so let's take a look at these values. So if you compare the values from f of x and L of x, you see that they're actually very similar, but the closer we get to 1, so as we kind of zoom in on our graph, the values become even more similar. So here, we're 0.08 away, so it's a decent approximation, but it's not perfect. But look at these values. The difference between 0.9702 and 0.97 is hardly noticeable. So the closer and closer we get to x equals 1, the more accurate our linearization is. So you'll notice that for all of these values, our linearization is actually a slight underestimate of our function. So that's not always the case. It just depends on which graph you're working with. Now, if you think of, again, let's talk about why this is happening. If you looked at what these graphs look like from the warm-up or from the last slide, here was one of our graphs. Here's f of x. And here was our linearization or our tangent line, L of x. So you'll see that everywhere except for that point of intersection, f of x is always going to be greater than L of x. You can see that our graph, our blue graph, is always below our red graph at any given x value. So whenever you have this scenario, your linearization is always going to be a slight underestimate when you are using it to approximate a value. All right, let's try one together. So we're going to find the linearization of this function, f of x, at the point a equals 2, and then we're going to use it to get an approximation for f of 2.1. So again, the linearization is really just the equation of our tangent line at that point of intersection. So let's start by finding our derivative. So this is just x plus 2 to the power of 1 half. So we have 1 half times x plus 2 to the power of negative 1 half. And we would use our chain rule, but the derivative of our inner function is just 1. So our derivative is 1 over 2 times the square root of x plus 2. So we want to find the slope of our line when a equals 2. So we'll substitute, and we get 1/4. So that's the slope of our tangent line. So now we just need to make the equation. So we know, again, that our slope is 1/4. And then we're finding the tangent line when a is equal to 2. So that's the coordinate 2, 2, if you substitute that into our original function. So we can use point slope here. And then here we will just solve for y. So it's in that slope-intercept form. So it becomes 1/4 x plus 3 halves. And then I'll simply write it as L of x because that's how we write our linearization of our function. So we just found the linearization of f of x. And now let's use it to estimate f of 2.1. So we'll do L of 2.1. And, you could do this with a calculator, but really linearization is useful when maybe you don't have a calculator to work with and you want something that's easier to compute than our original function. So let's treat 2.1 as 21 tenths. So we have 1/4 times 21 tenths plus 3 halves. So that becomes 21/40ths. And then we could rewrite this to have a common denominator. So it becomes 60/40ths. So that gives us 81/40ths. And that is our estimate of f of 2.1. And that is equal to 2.025. So we can compare it to the actual value of f of 2.1 just to see how close we are. So now let's actually do f of 2.1. So we have the square root of 2.1 plus 2. And this we can use our calculator and get a decimal approximation, and it becomes 0.0248. So you can see that it's actually extremely close to the actual value of f of 2.1. Now you will notice that in this case, our linearization is now an overestimate for this approximation. So let's talk about why this is happening. So let's do a quick sketch of our graphs. So if we sketch f of x, it's our radical function, but it's been shifted over to the left 2 units. So we have here, then we have this coordinate and this coordinate. We know that looks something like this. And then if you sketch a graph of this function, if at least in approximation, here's our y-intercept, here's that point of intersection, so it looks something like this. You can see that at any given point, L of x is actually going to be greater than f of x, except at the point of intersection where they are equal. So in this case, our linearization is greater than the original function, which is why we have a slight overestimation for our approximation. All right, so I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work. So here you can see, found the linearization. Again, it's just the slope, or it's just the equation of the tangent line at this point, 2, 8. So we get 12x minus 16. And so we can use that linearization to estimate f of 2.03, and we get 8.36. And if you compare that again to the actual value of f of 2.03, we get this decimal approximation, which is extremely close to our estimate. So in this case, this linearization was a good way to estimate that value. All right, That is all for today's video. Thank you so much for watching.